so much for the invitation, and I really appreciate it. Appreciate the Rice Gang for putting this together. Disclaimer, I think I'm one of the few chemists at this meeting. I've enjoyed really learning about a lot of the physics. So here goes. So I moved to Baylor about 2 years ago, and this is where my office is located. My X-ray lab is across the hall on the other side. And when we need some inspiration, we do go see the bears. They haven't been doing really well, but they're adorable. But anyway, so here goes. But before I give my talk, I want to share that, I have a lot of former students that have just been an inspiration to what we do for a living. Imagine telling a whole bunch of chemists that we're going to work on magnetic frustrated systems or really odd spin glass and spin liquid systems. Those are the terms that most chemists don't think about. But as a crystal grower, I'm definitely intrigued by the phenomena, and by which I'm going to share with you our approach to this effort. And this is also good for the students to know they could get jobs in this field. So that's always a good thing. All right. But anyway, we're very much motivated by the crystal growth to advance quantum materials, and we are at a great time to do this. I've been doing this for 20 years, and for a long time as a solid state chemist, I think about the structural features that govern and really that leads to the novel physics. And so I spend a lot of time reading physics papers, and sometimes there's a lot of nomenclature that is entertainment. But nonetheless, I do care about how things grow, and why should we, as a chemist, as a solid state chemist, spend the time to grow single crystals. And I wanted to reiterate the fact that that's actually quite non-trivial. It's one thing to show a crystal structure, but boy, along the way, we do find new materials that we just don't know what they are. And but it is necessarily nonetheless to fully characterize the system. So throughout my talk, you might see single crystals. I always tell graduate students and undergraduates too that these highly faceted materials are certainly quite satisfying, especially for a solid state chemist. For many years, I've been thinking a lot about, what are the factors that govern the physics of materials, especially with respect to local environment and dimensionality. And clearly from this morning's talks, and also earlier, right after lunch, we think about low dimensional materials. So certainly that's important. But what about the local environment? What about both? Okay, so those are the questions I ask ourselves. And so with the benefits of having single crystals, we could determine the crystallographic parameters. There's a lot to look at, not just atomic positions, but what about atomic displacement parameters? What about the chirality, for instance? So anyway, but take home message, you don't pay attention for the rest of the talk, is that discovery and synthesis really precedes applications. Absolutely important. So just like everyone else, we're very much interested in Kagome materials, and this has been a fantastic journey. And several collaborators and we did write a paper on why we care about this and what are the currently materials that is of particular interest, and some of them have been certainly highlighted at this meeting, and so that's always a lot of fun. But nonetheless, as a solid state chemist, I do look at local environment. So hopefully I'll be able to express that throughout my talk. I'm going to give you some examples of how we go about doing this. Okay, this is our periodic table. We did a inventory in my group, and we have used over 80 elements of the periodic table. Why not, right? But one of our ways to grow single crystals is to use low melting main group elements to grow our materials. And certainly relative to the transition metal and the lanthanides, the main group elements are relatively low melting, right? Of course, we don't buy gallium in the summer in Texas. It will melt. But yeah, here's our periodic table. So another thing I do is I avoid the actinides, okay? Actually not a big fan of arsenic. I want to keep my graduate students alive. I don't know how people do it in a physics community, but here goes. But we do take advantage of the fact that, thinking about the periodic table, we're going to take advantage of how we grow materials, okay? So this is just an example. It all began some 20 years ago. I decided to use antimony to grow another compound, and antimony melts at 600 something, and that works. We grew LASB2, which is great. It's known, okay? But what was fascinating to me was that there are these antimony sheets, right? And so turns out that it's a low temperature superconductor. And back then, you know, we don't think about square nets, but now we do. But the problem was, these are all low temperature, for the magnetic lanthanides anyway, they're low, you know, they're ordering at low temperatures. And so as a chemist, I was like, well, that's no fun. Who cares about 2 Kelvin, right? Well, now we do actually. So one of the things we started to do was, can we insert a transition metal in between the sublattice? And so that's exactly what we did. And this is a known structure type, the lanthanide, nickel, antimonite. And it turns out that it is quite a robust system, because you could grow a whole bunch of different lanthanides. You could insert a whole bunch of different transition metal at different concentrations. And along the way, we could also grow materials like the lanthanide, nickel, antimony 3. That also exists. But the common features is that you have these square nets, and interspersed between the square nets, you got either a tetrahedral or an octahedral environment in a transition metal. Now, of course, the tetrahedral environment got us excited in light of iron superconductors, for instance. But so those are the structural features we thought about back then. Okay. And again, do we know that we were going to make this? Not really, right? We wouldn't know it until we try it. And so that's what we got. But, you know, we make a lot of materials, but we have to spend the time to think about which one should we focus on. Okay, so hopefully I'll give you some examples of how we did make that decision. And of course, in more recent days, and we've seen a lot of papers in this area with square nets, for example, the tellurides and quantum Hall effect. Certainly that's something that is exciting in this community. But it's always good to think about this. You know, a lot of these compounds were discovered some 30, 40 years ago. And so the question is, you know, do we step back and think about, well, which one should we study? Okay, which one should we revisit? Okay, and the rich physics that can emerge just from these structural features, maybe it's something we should think about. Okay, so evaluating local environment is one thing, and this is another paper that I saw in 2010 that was kind of neat because of iron selenide, iron superconductivity, and you can see that there are certain structural features, and so for even people outside the field, you can see that okay, tetrahedral environment is important, and so these are the iron superconductors. And again, because we want to, you know, we think about things like, oh, well, can we increase the ordering temperature of some magnet, right? Or antiferromagnetic transition. The world doesn't need any more 10 Kelvin antiferromagnet. But anyway, so we dumped a whole bunch of iron, and what happens? It becomes, you know, again, you know, we have these square nets, and we got this bi-layer of these tetrahedral slab. And so one of the advantages of having something like this is that we can start to think about, well, can we stack them differently? How about dimensionality? Okay, so now we have another parameter, local environment and dimensionality. And this is just a demonstration of this. So what about stacking subunits? Okay, so in current literature, for instance, people are excited about heterostructure, right? We make these architects. So can we do this in bulk? Okay, that would be nice because we don't have to worry so much about interfacial issues. Okay, now some of these compounds, I have to admit, they can be complicated, but nonetheless, we had written a review paper several years ago thinking about, well, can we go beyond 2-dimensional materials? Okay, and in some ways, this is somewhat like Legos. Can we stack them in the right order? That's the question I always ask myself. We make them, we grow these materials, but what about the order? Can we govern the order of the materials and casting the wider net? But there are a lot of compounds that we should just be thinking about. For instance, last year we published a paper really inspired by the barium aluminum 4 structure type, which was theoretically proposed to have topological states. And we thought, well, let's just make a structural map and parameterize them. Can we use that map as a prediction of which compounds to make? And so with our interest in cerium compounds, for instance, cerium and ytterbium, because of highly correlated systems, we thought about things like cell volume, simple things like cell volume. And what about the transition metal? And can we, you know, can we make a map so that we could say, oh yeah, on this side of the periodic table, we should have cerium 3+. On this part of the map, we should have cerium 4+, for instance. And that's been a lot of fun. Okay. But so then the thought is that we had to go back to something we thought about. Okay. So Alan Shea posted this list. Okay. Cerium indium 3. And that was something that really started me thinking about this quite a few years ago. In the beginning of my career, actually, that was a long time ago. But this is the cerium indium 3. There's a gold copper 3 structure type. And essentially, you know, apply a pressure and you have an antiferromagnet that becomes a superconductor. That's great. And that's a cerium environment where you have 12 nearons. Okay, so that's a cubic octahedron. So then the question is, why aren't there many systems like this? Is this one of the few examples? I'm very much interested in magnetically mediated superconductivity, for instance. But then I thought, well, what about other compounds? And so that's one of the goals that we have as well. Are there other systems? And so we thought, well, indium, that's group 13 element. Can other cerium compound, for example, even with group 14 elements, can it also form these three-dimensional entity? Now we know from our antimony experiments, working with antimonies, that they tend to, make layered materials. And we thought, well, what about, group 14 elements? And in fact, as part of that goal, we actually make this compound. We published it in 2006, and we were excited to see this because it reminded us of a perovskite compound. And so this would be the first example of an intermetallic perovskite. So for which we were excited about. And if you look at the formula, it's ABX3, it's a triple perovskite. One of the 10 sites is on the A site, so ABX3. Okay. Now, thinking about this, of course, with cerium, we were curious what the capacity looks like. And in fact, this is one of the heaviest heavy electron system. In fact, it's 4 joules per mole Kelvin square. And every time I think about this, I have to think about the units. 4 joules is a lot. Okay. So, but again, in this crystal structure, you basically have 10, like I said earlier, one of the 10 site is in essence on the A site, okay? Now, 10 can be cationic or anionic. And so that's really nice because if you think about 10 being more cationic, then it should go to the A site, and the anionic part, which would be the polyhedral sites here, that would be the anionic part. It makes up the polyhedra, okay? It makes up the 12, coordinate environment, okay? So, and in fact, we sat around thinking, okay, what are all the 3, 4, 13 compounds, okay, that are known? And we wrote a review article about this. And it turns out that not all the compounds are centrosymmetric, not all of them are cubic. And similar to the perovskites, I mean, boy, they're depending on which elements, you can also have the distortion. And in fact, that was intriguing to us, okay? Looking at the local environment again. So in fact, what we did was, this was in 2006, and we revisited this, and looking at the literature, even in 2016 and 2018, we saw 2 compounds, 2 reports where, now this is a 3-dimensional compound where you see charge density wave. And coupled with this, there is a structural phase transition from a centrosymmetric to a non-centrosymmetric. So that was exciting to us, because then the thought is that, does that mean charge density wave? Does that mean we always have to have low dimensional entity? Oh, I can't believe I said this at this meeting. All of you have, quite a few of you have low dimensional materials. But anyway, work with me here. So that just tells you that, boy, even this sort of material, should we think about this? And would there be more compounds that really can envision, really fantastic behavior, especially with respect to charge density wave? And so one of the things that we did was, because we were doing data mining, okay, so one of our joys is, okay, so can we predict, okay? So instead of making every 3, 4, 13 compounds known to mankind, these Ramika intermetallic perovskite phases, one of my graduate students decided to think about the geometric descriptors that would be critical to predicting whether a compound, whether the cerium compound or the ytterbium compound, pick your favorite lanthanides, can we predict which crystal structure type? It turns out that the Ramika phases, there are quite a few of them. And there's the one that I just showed you, but there's this other one with a funny formula. But bottom line is, he made a map where we said, okay, yeah, so depending on the size of the lanthanide, something as simple as that, and the distortion, T represents, the height of the trigonal prismatic unit, icosahedral, that's the size of the icosahedron, that's the I part. Yeah, and he made this new tolerance factor, similar to what people in the perovskite community have done, but this is for the intermetallic. And another thing that was exciting to us is that depending on the lanthanides, whether it's cerium or ytterbium, we could predict, which structure type should have formed. Because if it is ytterbium 2+, for instance, that would be a larger cation, looking at the bottom of the periodic table, lanthanide contraction. So we're able to predict which structure type should have formed. And most importantly, the oxidation state, just by looking at this map. And there's still some refinement to do with respect to what are the critical parameters, but that's ongoing. So we thought, okay, so we want something that is, we think about things like, okay, so this is metallic. What about if we want something more insulating, right? So if you have tin, that's more metallic, yes, presumably. And so what about germanites? Can these germanites be made? And so that's what motivated us to do germanium chemistry for a while. Now, we did make cerium cobalt germanites, and the 112 structure type is known. Okay, it's been reported, lots of compounds, and we also make the praseodymium cobalt germanites. And basically, what we have here is that we could grow single crystals, and it turns out that this is a new homologous series. Okay, and now this new homologous series is exciting because some of the structural subunits are actually quite evident in known wild materials. And the yellow highlighted is the AlB2 type. If you tilt your head, you can actually see it. And another feature is that you got the barium aluminum 4 type, but now with the non-centrosymmetric subunits. And it turns out that with each successive end members, okay, we decided that this is going to be a new homologous series. Okay, just like if you think about Watson popper, or you're stacking all these subunits. Okay, now I do wanted to say too that with each. And actually, we could count the number of barium nickel tin type structure subunits. So in other words, the infinity member would be the cerium cobalt germanium 3 compound. Now, the thing is, when you have to grow single crystals, you really have to think about, well, can we distinguish them? Okay, and with these stacking subunits, it's very important to be able to say, okay, they all look the same. The crystals look the same. So one of the things we did was, you can see that, if we zoom in, we have to carefully evaluate the powder diffraction pattern to really think about what the structure should look like. Okay. Now, whether we have the right phase or not. Okay. So one of the things we did was I had 2 different graduate students spend time at a beamline to build a furnace so that we could do in situ X-ray diffraction measurement. So in other words, as a function of temperature, okay, because we can't tell, what is the best temperature profile, right? But if we do in situ X-ray diffraction, we could actually figure out, okay, what's growing at what temperature. And then that way, we could just use small amount of sample and be able to grow larger single crystals. So that was a lot of fun. And actually, the furnace is still at 11 BM. So someday when APS is up and going, and that will be available to the community, which we're really excited about, for the growth community. So we're able to get very nice powder diffraction pattern, even with tin. Tin actually absorbs, okay? I mean, for some reason, okay? But nonetheless, we're able to identify a new member of the series, and that's how we really decided that, okay, we now have a new homologous series to work with. But another thing we also thought about was, well, our student was at the beamline, and we had a ytterbium phase, and we thought, cerium, ytterbium, what do we have? And we had gotten a compound. It turns out that this is a hybrid of a cobalt tin and a 166 structure type compound. We have beautiful crystals, but the structure was more complex. And so we thought that it is important for us to really confirm our structure determination. We got nice crystals, but telling our students to grind those crystals up, oh dear. But you know what? We have to have complementary confirmation of what we think we got. Okay. And it turns out that if you look at the cobalt tin, which is a known phase, and we'll hear more about it for the next, we will hear about it at this meeting. But basically the hybrid structure is really a combination of both the cobalt tin and a 166 hafnium iron germanite. And if you look at the formula, it's like, well, so isn't that, that's similar to the hybrid, to the 166, but it turns out it has to do with filling the void. So cobalt tin, in this case, on the very left, you basically have these void space that are not occupied. Now I have to admit that I decided to hide one of the cobalt, okay, site along the Kagome nets, just for clarity, but they do exist, okay. But nonetheless, this has been a lot of fun because now we are able to say that, oh yeah, this hybrid structure is not, it's not 166, it's not cobalt tin, but it is a hybrid in a sense that here we have the rare earth occupying along the Kagome nets and also along the hexagons. Okay. So let me show you what this would look like. So when we do the refinement, basically we have, one of these 3 configuration, but it is an average of all of the 3 configurations. And so we're excited to see that this is, this is not just it's not 166, it's not cobalt tin, but that rare earth can be encapsulated. Now I also show this view because here, again, the germanium is on here, and then it basically, when you have ytterbium, it actually displaces the germanides. Okay, so we know that. And that's one of the considerations. Now, so in fact, with ytterbium, mostly it is, more or less 0.46 on each of the configuration. Okay. Now, and this is the this is the single crystal X-ray diffraction. Again, it's nice to have single crystals. We do diffraction measurements at room temperature. We confirm the cell. But again, because of the disorder, it was critical for us to really determine what we have, okay, by complementary methods. Now, we did the resistivity, and in fact, what we saw was there was an anomaly near 100 Kelvin. So it was proper that, okay, so this is, this is the one of the slab, okay, this is at room temperature. So it makes sense for us to collect the data at low temperature. So we selected 50 Kelvin, way below the anomaly near 100 Kelvin. And what we saw was the emergence of these superlattice reflections. So what that means is that you now have lowering of the symmetry, a structural phase transition from P6 upon MMM now to another lower symmetry point group, space group. So the most characteristic, most intriguing part about this particular 166 or half 33 compound is that unlike the other 166 phases, the cobalt atoms are actually not puckered up. In fact, all you see is the twisting. Okay, and that's unique. It's not up and down, but rather sideways. Okay, and another thing that is really neat is that the cobalt distances do not change. Okay, so it's actually quite rigid. Okay, and the only thing changed is the angles, but the distance are not changing. Okay, and so naturally, the cell dimensions would have to be double because it is for symmetry reasons, which makes sense. Okay, but it's only by low temperature methods that we say, okay, now we know what we have. This is exciting. But basically, this is an exciting platform, and we've been convinced of that today. But this is a lot to study. But we were thinking about, well, what about, can we govern how much rare earth can go into the site, and what about the size? Why is that? Why, the only other example that we have this twisting without the puckering is the magnesium cobalt germanite 166 compound. And so looking at this, we did recently reported this. We made the gadolinium analog. Now this time it's with tin. Okay, there are a lot of elements. Now there's so many variables. But what happens is the tin is nice because it's a low melting element, and so it could help us grow big crystals. But the problem is you also have tin encapsulated in this configuration, and it's actually quite large. This is basically the cobalt tin N member, closer to that N member, and that's a 40% configuration. This is the gadolinium version. And what we think what we decided it's really, we have to think about the size of the rare earth, and is it germanium or is it tin? Okay, that governs this. But boy, what a wonderful tuning parameter to see, and incidentally, we do not see any anomaly in the resistivity. Okay, just great, metallic system. Okay, and what we think it has to do with maybe the size. Okay, so maybe a smaller lanthanide perhaps. So in summary, I do wanted to point out that we're excited about making materials, but I think we're more strategic when it comes to making materials. We have to think about predictive methods, and I gave you two different structure types where we created these parameters and the structure map. But we also have to think about geometric constraint, and by which very detailed crystallographic parameters are critical. Okay, we would not be able to see this just by doing powder methods, and so single crystal growth is critically important. And of course, I showed you that how do we do this? In situ synthesis is wonderful because again, we only have to use a small amount of material, and we don't have to spend a lot of time doing this. And it's this really more effective way to grow crystals. And then the idea is that then we could create these maps for really designing next step materials. And that's been a lot of fun. So with that, this is my current group, and we're ready for Christmas. No, this is last year's Christmas picture, but this crew is great at growing single crystals. And then finally, I need to really thank all my collaborators. We have to rely on a lot of people to think about measurements, and even more recently mass power studies and everything under the sun, and then funding. And with that, I really appreciate the opportunity to present my work here, so I'll be happy to answer any questions you may have. Once it was very, any questions?
For the last programming material you mentioned, like so far there any knowledge about the best like
Not at all. I'm happy to have someone calculate. And so we are a pretty broke group. I'm happy to chat.
So thank you so much. So for the first part, we talked about these 3, 4, 13. You said maybe there's CW and could be 3D. So I'm trying to catch. There's something about the structure, the structural motif that suggests this two-dimensionality.
It's not two-dimensional. And so that was the point, is that, you know, if you have horizontal wave and a 3D material, so we don't understand that. And actually, we have found other compounds that I put up here, but where it has really strong bonding. Okay, I mean, and I thought the three-dimensional space, yeah, or even very, and a higher amount of property.
So is there any hint that you have about what makes those materials do that? Is it an elemental composition of the orbitals or
Composition and maybe the distortion of the local environment. Oh, this one I don't remember, like, but this is probably a 10 impurity. I'm not sure. No, I don't remember, actually. I can look it up. Yeah. They both make sense. But you don't say that it's negative. But you know, the funny thing about this gadolinium phase is that it is a higher concentration than the lower concentration. So the deuterium is actually close to 0.5 or half a degree, but the gadolinium is.
Good for the long period. I mean, I'd like to get a perspective actually when you talk about sync, right? So having to integrate some materials in life, right? So for instance, trying to create or synthesize some material on some CMOS technology, right? The problem there is most of the time it's materials at high temperature, right? So things are hurt. That's what people now they talk about low thermal budget, right? They have to put down into this synthesis like a low temperature. So what's your perspective actually? For instance, most of the beautiful materials now are created trying to reduce the synthesis temperature and then to integrate that kind of smoke.
Beautiful question. Yeah. So one of our ideas is that, you know, first of all, to grow the materials, you don't want to do infinite number of experiments, right? I mean, so that's one of the reasons why we're doing in situ. Because now we're doing in an order of 10 milligrams synthesis. But to answer your question, boy, device integration is almost impossible. But having said that, if we could think about understanding or predicting what compounds would be viable, then perhaps we could think about lower temperature synthesis methods. And actually, there are also alternate media to grow intermetallics. And so we have been able to grow intermetallics at 600-700 degrees, which is not 1100. Okay, so most of these materials actually turns out to be about 900 with the main metal flux. But we do think about that.
Just a quick question. So on these unfixed type materials, are there momentary ions?
Okay.
Which ones are?
Okay, so it turns out that gadolinium, obviously it's at 7, but cobalt actually also carries. For the gadolinium. For the ytterbium, actually, it turns out that the magnetic moment is less than what you would expect for a spin-only ytterbium 3+. And then, so the question is, you know, could it be that there's some 2+? But based on the ionic radii, and we looked at friends, should that be 3+? Or it's mostly 3+.